Determine the general solution for the following equation. Cos of 2x is equal to negative 1 divided by root 2. Now 1 divided by root 2 is an exact value that you should know for cosine. However, we could rationalise the denominator by multiplying by root 2 on 2 just to change that up slightly. So the equation that we're now solving is cos of 2x is equal to negative root 2 over 2. And hopefully you recognise that. So this does have a reference angle as we said before, and that is theta is equal to pi on 4 for the first quadrant. So pi on 4 is this angle here, and the cosine value read off the x-axis is root 2 over 2. However, you can see that we need the negative value of that, so we're going to be looking at this angle here and this angle here, both of which give negative root 2 on 2 as the x value of those positions on the unit circle. So because we're in the second and third quadrants, if this angle in the first quadrant is theta, the symmetry of this quadrant is pi minus theta, and the symmetry of this quadrant is pi plus theta. Therefore, we know that 2x, the bit inside here, must equal pi minus theta or pi plus theta as two specific solutions over the first period of cos of 2x. Therefore, 2x is equal to pi take pi on 4 or pi plus pi on 4. Therefore, if we evaluate that, we have 2x is equal to pi take pi on 4 is 3 pi on 4, and pi plus pi on 4 is 5 pi on 4. However, we're solving for x, so we need to divide both of these solutions by 2. So that will give us x is equal to 3 pi divided by 8 and 5 pi divided by 8. So far we've found x is 3 pi on 8 and 5 pi on 8 are two specific solutions. And those solutions occur if we go once around the unit circle. So if we go around to 3 pi on 8, that's that position. Or if we go around to 5 pi on 8, that's that position. However, if we were to continue and go around another time, so a further one period on the previous solution, we'd get another solution. And same for here, if we go around again, so if we go around another period, we'd find another solution. And we could go around infinitely many times, meaning there's infinitely many solutions to the equation cos of 2x is equal to negative 1 divided by root 2. So to help describe this infinite amount of solutions, what we need to do is work out what the period is. So the period of a sine or cosine graph is 2 pi divided by n, where n is this value here that multiplies by the x. So we have an n value of 2 this time. So that means our period is 2 pi on 2, which is just pi. So there's an interval of length pi between each of our solutions. So with the knowledge of the two specific solutions we've found, and that the period is pi, we can generate a general solution. We will have x is equal to a specific solution, 3 pi and 8, and then we're going to add the period on, and we're going to multiply it by k. And k is going to be any integer. So k could be 1, 2, 3, 10, minus 5, minus 20. It just represents that if you go a period further each time, you'll find another solution. Of course, that's only taking into consideration one of the positions in the unit circle. So we still have to write out the other one, which is going to be 5 pi on 8 plus pi, the period, times k. And again, we need to specify where the k value is an element of the integer set. So that just means, once again, that it could be 1, 2, 3, 10, 100, 1,000, or -3 or -7. So it just keeps indicating that depending on how many times we go around the unit circle, we're always going to find another solution. So this here is the general solution to our equation. So on this slide, we've got a computer to graph cosine of x in blue and y equals negative root 2 on 2 in red. So the points of intersection have been marked with little black dots, and this is 3 pi on 8, and 5 pi on 8, which were the two specific solutions we found within the first period of the graph. And hopefully you can see that if you go one period further on, so if you add pi, you get another solution, and if you add pi again, you get another solution, or if you were to subtract pi, you'd get another solution, or subtract pi again, and here's another solution. So this is where we added on k times pi to represent that there's lots and lots of values of x that give -1 on root 2. Of course, we had a second part of the equation though, and that was for the other specific value, and then we could add the period on to find a new value, and then we could add the period on to find a new value, or we could subtract the period away, and we could do that again to find the next value, etc., etc. So that's what our general solution represents. It's the two specific solutions, and then we add the period times the integer k to represent that there are infinitely many solutions to a trigonometric equation.